Actually, in writing this Zoom board, it's very difficult. So today I will take help of the notes, because I think today is my last lecture. So I will try to cover up at least one step methods. So
you can write side by side if you need.
yeah, if it requires, so
Yeah,
then
if
I will
it requires,
write.
you can use a side margin.
Yeah. Otherwise, it's I will try, because by notes I can cover little more.
Yes.
So we already have, I mean, seen that how we have generated these step marching methods, means explicit Euler explicit method, or forward method, Euler forward method, and Euler backward method, and trapezoidal method. So we can just combine that also. Basically, our motive is to get approximated this integral. This cursor is visible to you, ma'am?
Yes, sir. Cursor is visible. But
Yeah.
sir, I have one question. This is
Please.
from some book or it's your own notes?
It's not on notes. It's basically notes made by Professor Andre Suli. He's a
Okay.
professor at the
So can we get the? I mean, are they
yeah.
accessible to us?
Yeah. I think I can send
Yeah,
you.
you can share it, sir.
Yeah, I can
Please
share
share it.
you. But these are not my own notes. These are
Okay. So
by
that's what I'm
Andre
asking you,
Suli.
because
Yeah.
we want these notes, because it's difficult to write all the time. It's
Yes,
better
sir.
if we have.
Yeah. That
Okay, sir.
can. But
Please share it with us.
yeah.
Okay.
I will send. I will send.
Okay. Thank you.
So what I was discussing basically, so our basic motive to approximate this integral, am I right? And we did in the by the rectangular rule in the case of Euler backward or Euler forward, and trapezium rule by in the case of trapezoidal rule. So by these way we have done. So we can generalize this as a theta method, or all one parameter method. So how we do that? Generally, basically, what we are, I mean, if you might have observed that in the case of forward Euler method, we have took the contribution of the first node of the interval at xn, and in the case of backward, we have taken the contribution of the value of the unknown at the terminal node. And in the case of the trapezoidal rule, we both one. So then we can generalize, we can approximate who have exposure to the numerical approximation of integral. So in that case, so we have basically approximated this integral by this one, h times 1 minus theta, the value of the function at the initial node of the interval, plus theta times the value of the function at the terminal node. So in that way, now if we put theta is equal to, if we put theta is equal to 0, so then we will get forward Euler method. If we put theta is equal to 1, so then we will have the backward Euler method. If we put theta is equal to 1 by 2, so in that case we will have the trapezoidal rule. Yeah, so we have generalized, and we say that, okay, I mean, apart from this, we say that this is a one parameter family of the method, and we have taken theta belongs to the closed interval 0 to 1, and till the value of theta is less than half, so it will give you the explicit method. As it goes beyond that,
1 by 2 to 1.
Yeah. So then it will give you the implicit one. So this motivate. So this is a the method in that case, that y at xn plus 1. Here, if you look in this book, they have written it is an approximation, and when they replace this y by yn plus 1, so then they put an equal sign. And of course, yn plus 1, as we already discussed in the last lecture, that yn plus 1 not equal to y at xn plus 1. Basically, yn plus 1 is an approximation to y at xn plus 1. And same yn is an approximation of y at xn. So this is a theta method, we call it, one parameter family of methods. Yn plus 1 is equal to yn plus h times 1 minus theta fn plus theta fn plus 1. So yeah, they explain that if theta is equal to 1, so implicit we will have. If theta is equal to 0, then we will have explicit Euler, and theta is equal to 1 by 2, then we will have trapezoidal. And they solve, I think it's a very good example. If you look here, these are the I mean, this is the table. Basically, this is a table, and this is the first result is for is obtained by the forward Euler, and this is from the backward trapezoidal, and this last one is the backward. Yeah. So they have shown, and what is the exact where they have the exact value for that? This is for at 0, 0.1, 0.2, and this is the domain, at the domain the value. But somewhere
his example,
yeah, it's example. I have given today the assignment, so madam can give some question from that also. So basically they have the this is the exact. So this is the exact. Basically this is also some kind of approximation they have taken, but of course we treat it as the exact one, this one, because they have calculated here. So if we compare this, so you look in the table that this one is more closer to the exact for the trapezoidal rule. Am I right? For the same h we have calculated at 0.1, it's almost we are getting the same value in the trapezoidal, and at 0.2 also 1998. Yeah, so we are getting very close value. These are the very close to the exact root. So it means that trapezoidal is more accurate than the backward Euler and forward Euler. This thing is clear. And by the construction also, it was seems that trapezoidal give the better result than that. And this was the, and I mean by the numerical experiment also we observe. By numerical experiment also we observed that this thing is clear. But now we will prove the theoretical error estimate, which give us the which will give us the clear picture, and we can see that also. So we will start the error analysis of theta method. So first we will do for the Euler, and then we will generalize to the theta method. So global error, when we define, so what is global error? Basically En is equal to y at xn minus yn. This is the exact value, and this is the approximate value. So this is basically the global error, and we will try to estimate this for Euler backward, Euler forward, or theta, trapezoidal method, or in general theta method. So we will do that. And of course, I in the last lecture I have explained that how we generate a sequence of approximation here, and how it converts to the exact one. So that is important thing. So now we will do the error analysis. So we will start from the Euler explicit method, and then you can easily generalize to the theta method. So this is our method. Yn plus 1 is equal to yn plus h times f at xn yn, where n is running from 0 to capital N minus 1, and of course y0 is initially given. So then we define the truncation error. How we define the truncation error? Basically if we replace so what was the truncation error? If you observe the truncation error, if you observe, because now when we make the approximation, so then this inequality became inequality. It means that if you now differentiate left hand side and right hand side, and whatever value you are getting, of course that will be non-zero, and that is defined as the truncation error, because something we are neglecting, and because of that there was an error. That error is known as the truncation error, as I told you in the last lecture, if you remember. So basically here we define Tn in that way, that we write this yn plus 1 minus yn divided by h is equal to f at x and yn. Now what we did, we replaced the computed solution by the exact solution. Am I right? When we replace computed solution by exact solution, so then this equality will become inequality. Am I right? And the difference between the two sides will become non-zero. That non-zero quantity is known as the truncation error. The quantity obtained by inserting the analytic solution yx into the numerical method and dividing by the small size is referred to as truncation error. It is not only for the Euler only, it is for all single step method. Indeed, it measures the extent to which the analytical solution failed to satisfy the difference equation for this, in this particular case, the Euler method. Otherwise, we can say that the numerical method. So this thing is clear. So now please do one one calculation. So now here apply Taylor's. We can write this y at xn. We can write this y at xn. Even here I can write, I think, y at xn, or I will use. So in the side I can use that board. Hello, ma'am, you were telling something that in the side we can use that. Yeah, I think we can do that. We can take through this. Yeah, so now we will calculate Tn. What is basically Tn? Tn is equal to y at xn. So I'm just considering this one, this part, or then we will write that. So y, I can write y at xn plus 1 is equal to y at xn plus xn plus h, and now I am applying here the Taylor's method. So I expand this function y around xn. So what I will have, y at, I have y at xn. Yeah, xn plus h times. Yeah, h times y prime. Yes. Y prime at xn. Y prime is nothing but y prime is equal to f. So I can write that f, if you allow, f at xn. Okay. F at n means f at xn and comma y at xn. And then I will make minus sign. Now I am writing this one. So Tn here. So if I'm missing this, I can just do. So minus, I mean plus higher order term. I can say that plus the terms of order order h, or I should write, I think, one more term I can write.
Yes, h square you can write.
Yeah. Yeah, I can write one more term. So h square by 2, h square by 2, h square by 2 y double prime, and plus dot dot, or if you want you can write this Taylor series in the remainder form. This is xi
yes,
minus y at xn, am I right? Y at xn divided by h minus fn fn. So this is coming out to be this y at xn will cancel out, and this one h will cancel out from here. Yeah. Here, and one h will cancel out. So that is coming out to be 1 by 2 h y double prime xi. It's fine.
Yes, sir.
Yeah. So this is basically truncation error we are getting here. 1 by 2 h y double prime at xi n. Why they have written xi n? Because we are just considering the interval xn to xn plus 1 as interval change. So this xi will change. So where we have assumed that f is sufficiently smooth function, sufficiently smooth. What is the meaning of sufficiently smoothness? I mean belong to the derivative. Derivative. So it's sufficiently that, because here to have the meaningful of equation 19, so we need to have y double prime must be finite. Am I right? So y must belongs to C. So sufficiently means of two variable as, so which ensure that the second derivative of the y exists and is bounded in the interval. This thing is clear. So and order of a method is specified by the order of the truncation error. As I told you that in the I mean yesterday lecture, that convergence I mean does not only the truncation error. The truncation error, convergence include truncation error plus round off error. Both we have to address. But in this case, if we talk about that, because we are not using any machine, so there is no issue of round off error here. Only truncation error will play the role. Am I right? So that's why yes, h tends to 0. So this Tn tends to 0. So it means that our method is convergent here. This thing is clear. And how we define the convergence? That the power of h. If the power of h will be more, so as h tends to 0, then this truncation error will fastly converge to 0. So that's why order defined the, you can say that the speed of the convergence or rate of convergence also it is known as. So that's why I think in the later part in the notes it is given, but I have already explained that to you in the last lecture. So this thing is clear. So now, but basically we will take care of the round off error as well. So that why the global error will will consisting of two parts. One is the for the round off error, and another for the truncation error. But in the if you are not crunching the number, you are taking the exact from the number. So in that case there will be no issue regarding the stability of the method. So now this is a truncation error 19 given by the 19. So now by the Euler method, if we write Euler method in this format, which is in the format of 18, so then what we have, what is the Euler method? Yn plus 1 is equal to yn plus h fxn. So we have written this Euler method in that form. Take yn on the left hand side and then divide by h, and then take h to be left hand side, and we have written left hand side on the right hand side. This thing is clear? Yeah. So now why we have written this? This is because of some particular region to have the similar kind of this. Now we subtract this one from this one. Am I right? So on the left hand side we have Tn. Tn is equal to y at xn plus 1 minus yn plus 1, which I denote by en plus 1. Then minus sign y at xn minus yn, that is we denote e. So in the numerator we have that Tn is equal to en plus 1 minus en divided by h, and this and this fxn comma y at xn minus, because please just concentrate that
Please
this fxn, pardon, yeah, tell. Hello. Yes, ma'am. Yeah, so fxn y at xn is not equal to fxn comma yn. Are you agree? Because y at xn is not equal to yn. So that's why this difference. And then take multiplying h on both hand side, and then keep en plus 1 on the left hand side, and rest of the term on the right hand side. So I think you should all the participants should do simultaneously on your notebook. So then things would be more clear to you. So en plus 1 is coming out to be en plus h times fxn y at xn minus fxn comma yn plus h into tn. Now we are assuming that yn minus y0 is less than equal to, say, capital Ym. That can be done because in the second component, this is the function is Lipschitz continuous, so you can use you can use this in the we will apply here the Lipschitz continuity, because f is Lipschitz continuous in the second component in the y. So we can write that this thing is clear. So apply here the Lipschitz, take mode on the both hand side. Then you will have mode en plus 1 is less than equal to mode en plus s times mode of this one plus h mode of tn. This thing is clear. And then apply here the mode of xn y at xn minus mode of xn comma yn is less than equal to L times, where L is the Lipschitz constant, L times mode y at xn minus yn. This thing is clear. So then that it is coming out to be 1 plus because y at xn minus yn, we are denoting that as en. Am I right? So one en is sitting here and one en will h times l into en. En means y at xn minus yn. So that we also know this one. So we combine these two en and we have this one plus h times tn. This thing is clear. Let capital T, we are taking the maximum of tn. We can take that because it's a finite number. So a mod en plus 1 is less than equal to 1 plus hl mod en plus h capital T. Now by the induction and noting that 1 plus hl, just you expand this, you can expand that. So you will see that 1 plus hl 1 plus hl is less than equal to e raised to the power hl. So we just use that. We use that, and we have taken n equal to n minus 1 here in that one. So then we will have, and mod en is less than equal to t by capital L into 1 plus h l power n minus 1 plus 1 plus h l n power n and mod e0. So what we did, we start, I mean, if first you put here, just put n equal to n minus 1. So you will have on the left hand side mod en is less than equal to 1 plus hl into mod e n minus 1 plus h t, and then n start from, rather than 0, then n start from 1. Then you put the value of n minus 1. Because why we are doing that? Because we don't know en. Am I right? En we don't know, but we know E0. What is E0 basically? E0 is y. E0 is y at x.
Yes, sir. Now it is visible. Your screen is visible.
Screen is visible.
Sir, now. So here is you can see the pen at the top. To write something, you can use this pen. Yeah, this is what, right? Yeah, this, you just scroll down and see. It will allow you to write. You have to just select it.
Sir, you are muted.
Sir, please unmute yourself.
So you are not audible.
Yeah, now it's fine, I think.
Now it's
Yes.
So where I can.
Sir, this is where your cursor is there on the right of it. If there is your drop down menu, if you just find. Here is one. I can see the arrow. No, left.
This one. This.
No, right of this. This is what, and just below, slightly below this, your cursor. No, you are going to the left. So there's one pen. Now you can pick it up and then.
No,
So right, it's showing that there's a pen.
There is a pen sign. So where your cursor, you just see your cursor just a little bit above of this and right hand side. Just
No,
right.
I
No,
don't
sir. Again. Anyway, sir, you can explain it.
You can just write on the board, I think.
Yeah, on the board, no, sir. This is how you can write here also, on the PDF also.
PDF
Anyways.
you can write.
Yeah,
I don't think so.
we can write. Matlab, even we are using the same.
No, we can use then the PDF tool.
Yes, PDF.
By
On the PDF itself, you can write using taking the
By
pen.
the PDF, by the PDF we can write.
Yes.
Now, visible.
Then you don't
from
need board.
here we can write.
Yes. Please share your screen, sir.
Yeah.
Again, it is not.
Okay.
Sir, your screen is not visible. Please share it.
Yeah. Just now it's
Now it's
visible.
okay. Now
Yes,
it's
sir.
okay.
So we have this truncation error, and in that way we calculate it. So it is coming out to be this 1/2 h double prime. So you will see that the order of the convergence, which is defined by this is the consistency error, we can say that, and the order of a method is defined by the order of the consistency, mean the order of the truncation error. So it's coming out to be 1 Euler method. So now, but as I told you that we have to be careful of the round of error also. So that's why global error consists of 2, because basically when I put the value of that, so one power will keep increasing, right? So we will have this right hand side if you do calculation, so you can calculate. And also we know that mode I mean 1 plus HL is less than equal to e raised to the power HL by the formula of e power x. So then we replace this 1 plus HL, that will be equal to power n will be equal to e raised to the power NHL. Am I right? So we have written that. So this is coming out to be L, and the value of NH is xn minus the what will be the NH is equal to because h is equal to n xn, length of the interval, divided by the number of intervals. So that is coming out to be xn minus x0 minus 1 plus e raised to the power L, e raised to the power, here also we did the same thing, e raised to the power L xn minus x0 mod e0. So also we have bound on t, because more t is less than equal to 1/2 h m2, where m2 is nothing but is the bound, max of y double prime. So we replace that here in this one. So mod en is less than equal to e raised to the power L xn minus x0 mod e raised mod e0 plus m2 h divided by 2l into e raised to the power L xn minus x0 minus 1. So from here you see that this component is for round of error, and this component is for the truncation error. Am I right? The order of the method is defined by this one. So if E0 is 0, so when E0 will 0, when we are not using any approximate value of Y0. Once we feed, use the machine, so it means what would happen? As soon as we use the machine, we need to feed Y0 in the computer. Once we do that, so then it may truncate that. In certain cases, suppose its value 1, so it will take 1. But suppose its value is 1/3. So in that case, suppose y0 is 1/3. So in that case, it will take its approximate value of 1/3 rather than the exact one. Am I right? So that's why this E0 will then non-zero. So that's why it's this thing. So then using the same similar step, we can find the estimate for the theta method, and what type of error estimate we have for the theta method. Mod en is less than equal to E0 e raised to the power L times xn minus x0 divided by theta LH plus h by 2 mod 1/2 minus theta m2 plus 1/3 h m3. M3 in the case of M3 basically is the maximum of y triple prime. So this e raised to the power L xn minus x0 divided by 1 minus L theta LH minus 1. So now here you see, if we put theta is equal to 0. Put theta is equal to 0 here. So here you have theta is equal to 0. So 1. Am I right? So e raised to the power L xn minus x0. So you have the first term of this one. Now look the second. So we are putting theta is equal to 0. So once we put theta is equal to 0 here. So 1 by 2. Here we have 1 by 2 m2. Am I right? You multiplying this inside. So what we have 1 by 2 h m2 divided by L plus 1 by 3 h square m3. And of course, this factor will multiplying in both the factors. So we have this one. So the first one is this one. And the one more term would be there, that 1 by 3 h square m3 by L into this term. Am I right? But we once when we have the series in the error equation, when we have a series in h, so we will take its the lowest power. So lowest power in that case is h. So that's why the order will be specified by the first term. So we will have this one. Am I right? When you put theta is equal to 1 by 2, theta is equal to 1 by 2. So in that case, what would happen? In that case 1 by 2, this term will become 0. Now we don't have any term containing h. Am I right? What we have? We have 1 by 3 L h square m3 into this expression. So that's why for theta is equal to 1 by 2, the method is theta method has order of convergence 2. And for theta is equal to for other value of theta, I can say that between 0 and 1 except 1 by 2, this method has order of convergence 1. And for theta is equal to 1 by 2, the method is known as the trapezium or trapezoidal rule. So in the absence of rounding of error, as I told you, in the imposing of the initial condition 2, we can suppose that E0 is 0. And assuming that this is the case, so we refer that En is equal to of order of convergence is 2 for theta is equal to 1, and all other value for theta, the order of convergence of this method is 1. So this thing is clear?
Yes, sir.
Yeah. So now if you observe, I think in the table we have seen, so that's why for theta is equal to half, we are getting the better result. Am I right? What would happen basically if you look, when we see from this analysis that each time the mass size h is half, then what would happen? Then the truncation error and the global error are reduced by a factor of 2. By a factor of 2 in the case when theta is not equal to 1 by 2. And by a factor of 4, when theta is equal to 1 by 2. Because in theta is equal to 1 by 2, the order of convergence is 2, means of h square. So you put h value 1 by 2, so then the error will reduce by the factor 1 by 4. And in the case when the order of convergence is
Sir, you are not audible.
hello.
Yes, sir. Now you are.
Now audible.
Yeah. So that's, I think from here you would be able to understand the role of order of convergence. Am I right? So now if you observe, we observe in the 3 method, one is that explicit, Euler explicit, and 2 methods means implicit, Euler implicit method, and trapezoidal method. In both the 2 method, we have the unknown is given implicitly, and in the case of Euler forward method, the unknown is given in explicit form. Am I right? So to calculate the unknown, so then you have to have another, iteration you require to solve a non-linear equation. Am I right? You have to take another approximation, because in that case, if f is a linear, then it's fine. Am I right? In this method, trapezoidal method or implicit Euler method, if f is linear, so in that case, what would happen? We can extract this yn plus 1, and we will take it on the left hand side. We will combine with that, and we can write this in form of explicit one. Am I right? You will see in any book, you take any book by Professor M.K. Jain there, so where this f is a linear, so there's nothing to worry. But when f is non-linear, so then you have to solve the non-linear equation. Am I right? Then you have to apply some another approximate method like Newton's method. You will do that for solving the non-linear equation for yn plus 1. So that's why. But what you can do, that you can make this trapezoidal method in explicit form. What you can do that for writing, this. Yeah. For this value, what we will do, we will use the explicit Euler method. We will use here the value of this in explicit method, and then we have this method. Yeah, this one. So now this is a explicit method. Am I right? Order of convergence of this method will remain 2. Yn plus 1 is equal to yn 1 by 2 h. And we have taken here the approximation of yn plus 1 by the explicit Euler. Am I right? So then this is known as the improved Euler method. Why we call it improved Euler method? Because we have explicit Euler, but order of convergence, or we can say that not exactly it will be 2, but naturally it is improved. But when we can do the same thing in the implicit, but there if you do that, so there nothing we will achieve, because order remain the same. So that's why it is known as the improved Euler. Now can we write the general explicit one-step method? What is the meaning of journal? Means you think any explicit one-step method that can be deduced from a journal one. So we can define. So this is the more journal explicit one-step method, which can be written in this form. Am I right?
Yes.
In this form, and you take a particular value of this phi. So you will have another method. You think any explicit one-step method. For that method, you can specify the value of this phi. Am I right? For example, in the case of improved Euler method, in improved Euler method, the value of phi is this one. Am I right? Similarly, you can write for the explicit Euler method. For the explicit Euler method, what will be the value of this? Anybody can answer? It's Fn. Am I right? It's Fn. Phi is equal to Fn. So of course, then we can define the global error is the same. That difference between the two, approximate and the exact one, and the truncation error we will define in that way. In that way we will define the truncation error for journal explicit single step method. So, and for that, can we write the error bound? Yeah, answer is this. Consider the general one-step method specified by 22 means this equation, this one, where in addition to being a continuous function of its argument, phi is assumed to satisfy a Lifshitz condition with respect to its second argument. So can anybody answer that what is the relation between the continuity and Lipschitz continuity. There exists a positive element. I mean, we have continuity and differentiability. So there is a in between it lie. I mean, it is stronger than the continuity Lipschitz continuity and weaker than the differentiability.
Differential.
Yeah, so there exists. So that's why we are assuming continuous, but in the second component we are expecting more than that. Then there exists a positive constant L phi. This L is the Lipschitz constant, and it changes with the this. Of course, this function phi change such that for all h between 0 and h0, and for some region R is the region where the I mean y and x lies, as in Picard method, where the solution lie is. So this phi minus in y, if y minus z we are taking, so then it is less than equal to L phi y minus z in the second component. Then assuming, of course, we are taking this is bounded, so then we will use that mod En is less than equal to e power L phi xn minus x0 mod E0 plus e raised to the power L phi xn minus x0 minus 1 divided by L phi into T, where this is a capital T is the maximum of the truncation error throughout the domain. So I can skip this the proof, because
Yes, sir, proof. Yeah. You can share the notes with us.
Yeah. So then it is a second example. You can see it's very nice. Nice example. I would like to explain, but you can do that, because just they have seen that how we can utilize that bound if we know the bound here. Okay, I'm just emphasizing little bit. Suppose for this particular example, so if we know this error in advance, so how we can utilize that? That is important. So that I will explain that part from here. Thus, given a tolerance TOL is specified. What is tolerance? As I told you that it is. I mean, user can give the tolerance because specified beforehand. So we can ensure that the error between the unknown analytical or exact solution and its numerical approximation does not exist this tolerance by choosing the step size. Am I right? If we would be able to know this En. Am I right? This thing. So we will take that, that this is less than equal to, this is less than equal to TOL, and from there we can find the value of H, because H is in our hand.
Yes.
So that's why we can use this. If we know this before computation, we know the error, so that can be used. Am I right? So in that way, we can use that. Consistency they have explained. So whatever I discussed in the last, the numerical method is said to be consistent with the differential equation if the truncation error defined by, as we already defined, is such that for any epsilon greater than 0, there exists a positive H, which of course depends this epsilon, for which mod Tn is less than epsilon for all H lying between 0 and this H epsilon, and any pair of point in the region R. Roughly, I think you can say that as H tends to 0, if this Tn tends to 0, so then we say that the method is convergent. Oh, sorry, consistent. Am I right? So, yeah, this theorem ensure the convergence. This theorem does not tell the convergence. This tells the, sorry, this is the definition, consistency. But the theorem 5 gives you the convergence result, because here we are not talking about the Tn, we are talking about En, basically y at xn minus yn. This tends to 0 as h tends to 0 and xn tends to x. Xn tends to, because as to suppose you have a 1 point x in the domain. So if you are changing your step size, if you are taking a bigger step, so you will reach at x early. If you are taking smaller steps, so then you will reach up to x, I mean in more steps. So that's why in that way you will also generate a sequence xn, and as x tends to I mean this x, this difference must go to 0. So I'm skipping this proof also because we don't have the time. And order of accuracy or order of convergence, we already explained that the numerical method is said to have order of accuracy or order of convergence p if p is the largest, p is the largest positive integer, such that for any sufficiently smooth solution curve x comma yx in R of the initial value problem, there exists a constant k and h0 such that mod Tn is less than equal to k times h power p. Then we say that p is the order of convergence of the method. So whatever method we have developed till now, I mean all these methods have order of convergence, maximum order of convergence 2. But I think before developing these methods, I mean when we are talking about talking about these Taylor's, the method generated based on Taylor's I mean approach or Picard. So there, I mean, what was the beauty of the method? That we can have the desired accuracy. Am I right? But here we are able to do that only up to order 2. So now I mean we wish to basically increase the order of convergence. Or we can say that accuracy we wish to. Accuracy. So to do that, I told you in the beginning that in the approximation theorem, in approximation theory, the distrust theorem play an important role. Then for any continuous function, we can achieve or we can approximate that function by a polynomial with a desired accuracy. And how we will get the desired accuracy? Increasing the degree of the polynomial. Am I right? So same thing, but if you observe in all these three cases, three methods which we have derived, so we approximated the curve by a straight line. Am I right? Yes. By a straight line. So we want to, I mean, increase the accuracy of the method. So what we wish to do that. So we wish to do that we should approximate the function by the higher degree polynomial rather than the straight line. Am I right? And for that, what we require, because till now we require two information at the both end, means y at xn is, I mean we have, and y at xn plus 1 we have. So if we are using these one, so two information. So by using these two information, we can, I mean, fix a straight line only. Am I right? Because ax plus b. The equation of the straight line is ax plus b. So to fix a straight line, we have to fix a and b. So we require two information. Am I right? If we want to fix a quadratic polynomial, so then we have ax square plus bx plus c, 3 parameters. So at least we require 3 conditions. So I mean, to do that, we have 2 ways. Now one way, as I told you in the last lecture, when I was explaining that single step and multi-step method, that we have more information, but we are not using, because in that case our stencil is going, I mean, bigger one. But of course, when I want to increase the accuracy, so then I have to use that. So I can use that. So then that way goes to the multi-step method. Is there any? I mean, in single step method can also be increase the order of accuracy. Then the answer was given by the Ronje. Ronje gave the answer to that question. What he did, he used some fictitious node in between. If you are aware about the Gaussian quadrature formula for the integral, he used that concept, and he introduced the fictitious node between the xn and xn plus 1, and he have taken into consideration of that, and using that he increase the degree of the polynomial which approximate the function, and in that way he get the better accuracy. And in multi-step method, you people already aware about. In R stage, so due to lack of time, so just I'm quickly explaining the general R stage method is defined by yn plus 1. Yn plus 1 is equal to yn plus h phi. So in this case, what will be phi? Because it is, we are talking about explicit Runge-Kutta method, and why I mean there are two names, Runge and Kutta, two mathematicians. Runge did this work for the scalar. I mean first single y prime is initial value problem, and Kutta then extended these method for a system of initial value problem. So that's why at the end the method is known as the Runge-Kutta method. So phi is defined by this one, means now R is running from 1 to R, CR, KR. And now if you observe here that rather than taking this AR basically give the point in between the interval xn to xn plus 1. So it will give you the R point. Now we are taking the contribution, not only the end point, in the in between point also. And then they develop that method. One stage Runge-Kutta method is nothing but it's a Euler, forward Euler method, and two stage Runge-Kutta method you can obtain in that way. Just calculate the value of these C1 and C2. So how many parameter you have here? So you have here 4 parameters, C1, K1, and C2, K2. Am I right? 4 parameter. And then using some error analysis, so they try to obtain 4 equation, but unfortunately we were not able to obtain 4 equation. We generally used to obtain 3 equation, and in 4 unknown. So it means 1 parameter family you will have. So 2 stage. That's why it is written that 2 stage Runge-Kutta methods, not method. Am I right? So we have the 1 parameter family for that, which implies doing this calculation. So they are able to do that, achieve these or find these, fix these parameters. Then the method is a second order, and of course it is a second order convergent method. And you see that if you take in this 2-stage method, 2-stage RK method, if you take because 1 parameter they keep in that A2. If you take A2 is equal to 1 by 2, so then we are getting modified Euler method. If we are taking A2 is equal to 1, so then we are getting the improved Euler method. And I told you the difference between the improved and the modified, just we are modifying that one. And in improved, we are getting the better accuracy. So that's why this is a difference between the modified and improved one. And this is very good example. You can try. I will provide the notes at the end.
Please mute yourself.
Xn is this one, be a uniform mass on this interval of this size, because consider explicit 1-step method for the numerical solution of this initial value problem, which determine the, of course, approximation yn to the exact solution from this recurrence relations. And then what you need to do, then show that this method is consistent. So what you need to show, you need to find the truncation error, and then you show that as h tends to 0, if tn tends to 0, so in that case method is consistent. Am I right? So you see that you will find tn in this format. So as h tends to 0, right hand side tends to 0, so that's why the method is consistent. And of course they are asking some optimum, because alpha is involved here, so we will take a particular value of alpha so that we will have the more order of convergence. So you can do that example. So, and RK 3-stage method. So in RK 3-stage method, we have this is a general form RK 3-stage method. Ma'am, I will just take 3-4 minutes
No issue,
more.
sir. No issue. You can.
Yeah, so yn plus 1 is equal to yn plus h c1 k1 plus c2 k2 plus c3 k3. In this we have 6 parameter involved, and we will try to find 6 equation, but same thing would happen here also. We will be able to, we will not able to have the sufficient number of, or we will not have the square system. So then we will have some family of parameters here also. So they have given, I mean, different name, and you will see that once how many equations we have here. This is 1, 2, 3, 4. So 4 equations. So here we will have 2 parameter family. Am I right? 2 parameter we need to fix, or 2 parameter family of 3 stages. Am I right? 2 parameter we need to fix. So then we will have a square system. Am I right? 4 equation, 4 unknown. But unfortunately here you see that it is a system of 4 equations, but equations are in unknown are this is a system of non-linear equation. Am I right? Because the square is sitting here, even here multiplying there, and here. So that's why it is very complicated. If you go 4th order, RK4, so then it will be, and if you go higher order RK method, so then it is very complicated to drive. Am I right? So this is a RK4. So K1 plus 2, K2 plus 2, K3 plus K4. Am I right? So we can find that also. But I think I expect one answer from the participant. I think in most of the cases, you might have heard that RK4 is the most popular method among all RK methods. So why it is so? Anybody can answer? Yeah, because actually in this case we get the for RK4 stage RK method, we get optimal order of convergence. What is the meaning of optimal order convergence? If you observe till 4 in RK1, the number of function evaluation is 1 and order of the method is 1. In RK2, number of function evaluation is 2 and order of
accuracy is more. No?
In 3, order of number of function evaluation 3 and order of convergence is 3. And in RK4, number of function evaluation 4 and order 4. But after that, it would not happen. Am I right? It would not happen. If you see RK5, in RK5, number of function evaluation is 5. Order is 4. Am I in 6? In 6, number of function evaluation is 6.
And it is 5.
Order is 5. That's why so in that way it is optimal. Because our objective that we should achieve the maximum order of convergence.
Accuracy.
Yeah, accuracy, but it should be optimum in that sense, because we need not to do more computation. But here we are doing more computation in the 6, in the 7. 7 you see 6, and if you go for R greater than 10, then the highest order is R minus 2. So this thing, and absolute stability of RK method is discussed. So that is we can cover right now. So I think I should stop here. So any doubt, anything, anybody can have?
So thank you very much, sir. for the last 4 days, we were listening to you and your methods for evaluation of numerical methods for IVPs and development and analysis of continuous approximate methods for IVP, and all the concept which you explained were so informative, and we got everything what we need for our further studies. So before we conclude for today, I will ask Mrs. Harindri Chaudhary, the convener of the event, to say a few words, because it is last day for Professor Kapil Sharma. So formal vote of thanks is required.
Yeah. Thank you, Usha ma'am. Am I audible?
Yes.
Thank you, Kapil sir. The way you have explained Picard methods, Taylor methods, Euler methods, improved Euler method, explicit methods, and modified Euler method, and today you explained just now Runge-Kutta methods and their optimal order of convergence is phenomenal. Thank you very much, sir, for the excellent conduct of lecture series into DA 2021. I do hope that this association, that is Deshbandhu College and South Asian University, will go a long way. Thank you very much, sir.
Thank you. Thank you.